Okay, hello everyone. Really nice to see that we have so many people here in the audience, and I guess many of you also following it on YouTube or something like that. This is the first GeoWednesday this semester, and it's the fourth year actually, so it's become quite a tradition, which we have. It's a collaboration between Department of Geoscience and the Science Library, and we are now in the Science Library. So today I have the great pleasure to introduce Frans-Jan Parmentier, which I always pronounce wrong, I think, but he's a 50% researcher here at the University of Oslo. He's affiliated to the Department of Meteorology and Oceanography, and then he's 50% associate professor at in Geobiosphere Science at University of Lund. So Frans-Jan, he holds now, and maybe if some of you have heard his name, otherwise not within Arctic science, he's also writing for Klassekampen, so maybe some of you have seen his name there. So he's frequently writing for them. Frans-Jan holds NFR project, a young research talent, Winterproof. It's not particularly that project he will talk about today, but more his Arctic life. Frans-Jan has a very long experience from working in Arctic areas, from northern Siberia through Svalbard and Greenland, and I think today he will take us through his Arctic life. So, please.
Okay, thank you, Britt-Lisa, for that very nice introduction. So today I would like to talk about Arctic ecosystems and their role in the climate system, and how they're really this thin green line between the soil and the atmosphere. I'd really like to thank the designer that made this flyer, made it look really great. And you might be wondering, when you look at this, this nice picture here, where that actually is. And it's the first step in a journey that will take you through the Arctic of different places that I've been to. Actually, this picture was taken in northeast Siberia. It's the first place I went to in the Arctic during my PhD. And it's called a Kitelik Nature Reserve. You see on this picture, you see Roman Savronov, who's a botanist from Yakutsk, and Daan Blok, who at the time, just like myself, was a PhD student. I was at the Vrije Universiteit in Amsterdam, and he was at Wageningen University. And we were there to study this ecosystem and see how it's changing. But it's you might not be very familiar with your different nature reserves in northeast Siberia. So for those of you that don't know where this is, let me just do like this. So for those of you that don't know where this is, so we're here in Oslo, all the way on the left, and this research site is. When I went there, it always felt like being at the end of the world, and it basically was, because it's all the way here. So it's just 100 kilometers off from the Arctic coast, and to give you a little bit of frame of reference, it's about as far north as the North Cape, and it's further east than Japan. So it's not so easy to get there. If you would want to go there, you would first have to fly to Moscow. Then from Moscow, you have to probably change airports. And make your way to Yakutsk on a second flight, 6 hours. And usually when we would get to Yakutsk, we would spend a couple of days there. First of all, to get rid of our jet lag, because that's already an 8-hour time difference. To the tundra, it's even 2 hours more. But also to meet up with our collaborators in Yakutsk at the Institute for Biological Problems of the Cryolithic Zone that accompanied us onto the tundra. It's actually, we were not allowed as foreign researchers to go there alone. We always have to be accompanied by a Russian, because according to, in Russian rules, even if you're 100 kilometers from the coast, which is then the border, is a military zone, so you have to have special permission to go there. So this final leg was in an airplane, an old propeller airplane that was actually older than myself. Flying to the capital of this particular region, which is called Chekurdach. And it's this little town on the tundra, but it's the largest settlement for hundreds of kilometers. And there's only maybe 1,000 or 2,000 people living there. So far, actually, it's the easy part of getting there. So it's just a couple of airplanes, and if you're not scared of old Russian airplanes, then you're fine. But from here, we actually had to set out in the tundra because our research site was still 30 kilometers away from here. In winter, that would look something like this. This is a picture I like to show because it's nice and it has some setting sun and everything. And here we would actually be passing the last tree. So we're going to real tundra. There are no trees at all. But this is also a little bit, I mean, from this picture you can't see that it's actually minus 20, minus 30 degrees. And we're sitting on a sled behind a snowmobile and basically getting, first time I went there, I got a little bit of frostbite. So it's actually quite dangerous situation that you're putting yourself in. And under these conditions, at least you know where you're going, but you can also get stuck in a snowstorm. This happened one year. You see, I see myself here. I learned to cover myself very well, like nice and warm after that first time. And basically what happened here is that the locals didn't know where we were anymore and which way we were going because they could only see 10, 20 meters out into this snowstorm. And they couldn't see the beacons on the hills anymore. We basically just had to wait until the snowstorm settled. We were lucky that time. Within an hour, it became clearer. We could see the hills again, and then we could continue on our journey. So compared to this, going there in summer is a lot easier because then you can use the rivers. So you go on a speedboat like this one, and you make your way to the tundra. They go very fast, but you need to go through a detour. So just like with the snowmobile, it takes you about 3 hours to get there. And then once you arrive at your location, then you're finally there at the Kittelik Nature Reserve, and this is what it looks like. So you see a couple of huts here in the distance. These are mostly old fishermen huts, but at the end of the 1990s, this area has been transformed into a nature reserve, and actually the German WWF put up a nice little house here for people to stay, and also for local school children to be educated about the nature in this region. We would often stay in this little blue building here, which was just 12 square meters, and we would sleep there with at least 4 people, and it was also a laboratory. So accommodations were very limited, to say the least. So we were happy to go outside, but when you were outside and it was a little bit of warm, working conditions were like this, you would be covered in mosquitoes because they would be everywhere. So considering all this long journey that you have to make to get there, potentially dangerous, and then when you're there, the working conditions are like that. Why would a Dutch guy go all the way there? Why doesn't he go measure in a nice polder or something? Well, I actually did during my master's, very close to the university, with very much the same equipment. But the reason that I went to the Arctic to study what's going on there is because climate change is amplified in this region. If we look at the temperature change across the globe, this is the temperature anomaly for the last 10 years compared to the temperature average from 1951 to 1980. And then we see that in the Arctic we already crossed more than 2 degrees of warming, up to 4 degrees. So this is a region that is warming very fast. And that also means that we'll expect more changes to be happening than further south, like here or in the Netherlands. If we look at this warming from another angle, straight down onto the Arctic, then we see that this warming is very much concentrated around the North Pole, and it's especially the tundra region that is warming very quickly. And that's the same area where we also find a lot of permafrost, that's permanently frozen ground. And then when these temperatures are rising so rapidly, that means that this permafrost can thaw. And that means that a lot of changes will be happening in the landscape. It can get wetter and drier. This affects the ecosystems also, and the entire landscape will change. And just to give you an example of how fast this region is warming, last June in Vergiansk, this is actually a town I would fly past on my way to the tundra. It's used to be known for having the record low temperature ever recorded in an inhabited place on the planet of more than minus 70 degrees Celsius. But now it's known for measuring the highest temperature above the Arctic Circle. And they measured 38 degrees there last June 20th. And this is a tremendous change that we're seeing that I couldn't even imagine when I started my PhD. And it's, you might also have heard of a lot of forest fires that broke out last summer this is actually that same region where all these red dots that you see in this picture are forest fires. And my old research site is actually right there, covered under the smoke plumes. Now, these are very clear impacts on the ecosystem when it's getting destroyed like this. But what I'm talking about today is not so much about fire. I'm talking about what's beneath the ecosystem and how the ecosystem interacts with that. Because when you're standing on the tundra, you might just see this nice green vegetation like on the flyer. But underneath it, we have permafrost. This is a picture that I took next to a permafrost lake at our field site. This is a lake where the lake is sort of eating into the lake shore, and it's exposing the permafrost there through a process called permakarst. So you can actually see what's going on under the vegetation. And so you see here on the top, we see the vegetation itself, and then beneath it is something that we call an active layer. This is the part of the soil that thaws each summer, and in the winter it refreezes again. And there's a lot of biogeochemistry happening in that layer. And then beneath that is the permafrost. And you can actually see that it's very shiny, and that's because this is just frozen ground. It's frozen mud mostly. But the way this always often reaches the headlines is, for example, just this week, when this was actually found in the permafrost. It's a well-preserved cave bear. This was found just 200 kilometers north on an island, just 200 kilometers north of my old research site. And they estimated that this animal had died somewhere between 22,000 and almost 40,000 years ago. And you can see that it's still very well preserved. You can see even parts of its fur here. So this is sort of the preserving power that permafrost has, that it can, that organic material that is contained in it is basically kept intact over time for even tens of thousands of years. Now, this is the sort of the flashy news headline version of permafrost. In this location where the permafrost was actively degrading, I was trying to find fossils myself also, and encouraged by a Russian friend that actually found the horn of a woolly rhinoceros. I did my best, but I couldn't find anything there. So for me, permafrost carbon, it's mostly this brown mud that you see on the left, because that ground also contains a lot of carbon by plants that have been growing, and when they die, their plant material ends up into the ground, and this is contained into the permafrost. And this is also a process that's been going on for tens of thousands of years there. So, so if this is all contained in the permafrost, that's nice. Not much would happen to it, you'd think. But of course, that's not anymore true in a climate system that's in transition. So if we have our look at what kind of how the carbon gets into the system and out of this system, we have uptake of carbon by plants, and in the soil, this carbon can be decomposed by microorganisms, and they respire the carbon back into the atmosphere. And our worry is that as climate change increases and these areas are warming, that this active layer part of the soil will deepen into the real permafrost part, and that will actually get a release of this previously frozen carbon. So this ancient carbon that was stored there by ecosystems eons ago might be released back into the atmosphere. Now I'm not mentioning a lot of other processes that are going on with permafrost also, like what you see on the right, for example. That's this permakarst that can actually also have a very large impact on how much carbon will be released into the atmosphere. Today I'll mostly focus on what the ecosystem does, and with the kind of technology that we monitor ecosystems across the globe. Because my site and other sites that I've worked at are part of a global network called FluxNet. And this is this is from a paper that was just published this summer, showing the true data set of all eddy covariance towers, and I'll explain what that is in a moment, of eddy covariance towers across the globe. And these towers, they are used to monitor what's happening to ecosystems. But when you look at this map, you can see Čekurdah or the Kitolik site indicated there on the top right. Then you immediately notice that that's in a region where there are very few observations. Almost all of the observations with these towers are being done in Europe and in the United States, basically where all the research institutes are. And this is an updated map. When I started my PhD, this was even worse. So there's, even though we have this region where we have permafrost, and there's a tremendous amount of carbon in these soils, there's enough carbon in permafrost to, if it would all be released, that doesn't happen at once, that's not physically possible, but the amount of carbon that's stored into permafrost is enough to double the amount of CO2 in the atmosphere. So even if only a fraction of that is released, it can be a positive feedback onto climate. So this is one of the reasons that I went to the Arctic. It's changing very rapidly. We have a potential for a climate feedback, and there are not that many observations. So this is the kind of instrumentation that I use to do these observations. I'm climbing here in a meteorological tower that does some basic meteorological measurements, incoming and outgoing solar radiation, for example, air temperature and wind speed. And I think in this picture I'm filling up a water bottle so we can actually measure also wet bulb temperature, which we can use to determine the relative humidity of the air. But the main instrument that we used here is the tower on the right next to the solar panels, which is the Attica Variance tower. Just to show you a little bit of a zoomed in version of what that looks like. So this is the instrumentation up close, and what you see here in the middle, this device with these prongs, that's called a sonic anemometer. This is a device that can measure wind speed at a very high frequency at 50 hertz or even higher, and in 3 dimensions. And we can use this actually to characterize the turbulence in the air. Next to it, this white analyzer that you see here is an analyzer with which we can measure CO2 and water vapor in the air. And with that combination, you can start to figure out how much CO2 and water vapor is exchanged by this ecosystem. But we can also measure other gases. On the left, you see an intake tube where air is actually being sucked in, and it goes down to an analyzer that's in this big box here. And then in this white box, there's a huge pump that's sucking down the air through this line, because you need a very large air sample to be able to measure these trace gases. In that box, we're actually measuring methane. I've done a lot of research on methane emissions. I will not talk much about that today, because I would be able to fill another talk about it. This technology is being used across the globe to measure the exchange of carbon from ecosystems. And so we do these measurements of very high frequency, and then we use some math to figure out how much is coming out of the ecosystem. Now, I will not show you the equations. I'm going to try to explain you how Attica Variance works without showing any mathematical equations. So bear with me. So if we have, for example, wind coming from left to right in a normal situation, then the amount of CO2 that's in the air measured at our Attica Variance tower depends on how much the plants here are photosynthesizing. Because these plants are, while they're photosynthesizing, they're taking carbon out of the air, which means actually that close at the surface, the amount of concentration in the air will be a little bit lower than higher up. And we can use this difference, not by measuring whether the wind is going from the left to the right, but how fast the wind is going up and down. Because when we look at wind, and you've been able to experience that outside, that wind is very turbulent. It doesn't go in a straight line. It looks more like this. So this is what we call eddies, these swirling motions in the air. You can have large ones and little ones. And when these motions, when, for example, a parcel of air goes with one of these eddies down, then it will be in contact with the vegetation. Vegetation will draw out some CO2 from the air. And then on its way back up, it means that there's a little bit less CO2 in the air. And we can use this difference if we measure all these eddies at a very high frequency while they're passing our sensor. And by measuring how much CO2 is going up and how much is going down, we can then determine how much is being exchanged by this ecosystem. So if you do that right, you'll end up with a measurement that we call net ecosystem exchange, which basically just means the net exchange of carbon or CO2 from this ecosystem. And there are two major components to that I already told about before, but I'll give you the official titles now. So there's gross primary production, which is basically the same as photosynthesis, so plants taking carbon out of the air, and ecosystem respiration, which is not only microbes in the ground that eat up the carbon and turn it into CO2 and emit it back to the atmosphere, but it's also a little bit of maintenance respiration by the plants themselves if they have, for example, damaged tissue and they need to repair that. So these three components make up our carbon balance. Now, at the end of my PhD, the tower had been there for a few years before I started, and then at the end of my PhD, we had 8 years of data. And then I could finally look into some trends, like how is this system changing while it is warming? So that's what I did. So this is from a paper of mine from a while back, where I show on the y-axis, so you see the amount of gross primary production. So that's photosynthesis, and we plot this negative because we're drawing CO2 from the air. So the more negative it is, it means there's more photosynthesis going on. On the horizontal axis, you see the temperature sum of the summer. So basically, the further to the right, it means the summer was warmer. And you can clearly see that with the warmer summers, we get more of this uptake by the vegetation. This makes sense because if we have warmer conditions, the plants can actually grow better, so they'll also be photosynthesizing more. But at the same time, this respiration that's going on, that depends on these microbes in the ground, they're more active at higher temperatures as well. So respiration showed the opposite pattern, where we had an increase with warmer summers also. And you might already see it from these graphs, but if we look at the balance, is net ecosystem exchange. Actually, we saw no change. So this seems like a sort of a good thing, that we have an increase in respiration because of warmer summers, but it's offset by the amount of carbon that the plants are putting into the system. So this is an indication that the carbon is being cycled faster in the system. Now we see also other changes going on in winter, for example. Winters are warming very quickly also. And in winter, plants can't compensate for any kind of carbon loss. So the winter might be the key to figuring out whether these ecosystems are actually losing or gaining carbon under climate change. This is, of course, a result from just one location in the Arctic, but it's actually a lot of other sites that now have these long histories have been able to show the same thing. Now, the warmest summer that you see here, all the way on the right, that was actually with the large arrow bars. So, for example, this year, that's actually 2007, and that's the first time I was on the tundra there. And 2007 was also a special year because it was a year where there was very little sea ice left. This, at the time, was quite shocking because it was a very sudden drop in the amount of sea ice, and it only was surpassed twice in 2012 and actually this year. But when I came back home from fieldwork and I saw this on the news, I was not only surprised to see that there was so little sea ice left, but actually, so my old field site was here. Most of the ice was gone just north of it. So I was starting to think like, hey, might there be a connection? We've had this crazy warm summer, we're seeing less sea ice, and of course, higher temperatures melt more sea ice. But there's also a feedback mechanism here that kicks in once the sea ice disappears. And that's because if sunlight hits sea ice, most of it's being reflected back into space because it's very bright. But if sunlight hits open water, which has a much darker color, then only a fraction will be reflected back into space. This means that the ocean can warm up, and this feeds back into the atmosphere. It's actually one of the reasons that the Arctic is warming much faster than the rest of the world. So this is a feedback mechanism where changes in the ocean can then affect the land. And in fact, 80% of tundra is only 100 kilometers away from the coast. So this means that this ecosystem is very much influenced by what's happening in the ocean. And we can see this in long time series also. So if we look, for example, at, this is from a paper of mine from a few years back. If you see on this graph on the top, that's sea ice, and I've plotted it upside down, so the higher it is, it actually means that there's less sea ice. And then you can see that the summer temperatures, the red line, are following the same pattern. So we have less sea ice and warmer summers. Then on the bottom you see two lines called maximum Ndvi and time integrated Ndvi, and they're changing in the same direction. And for those of you that don't know what Ndvi is, it's something that satellites measure to determine the amount of live biomass in vegetation by using a trick of seeing how vegetation reflects infrared radiation versus how it reflects the red spectrum of sunlight. So this is a proxy for the amount of biomass, and we can monitor this across the Arctic. So what's going on here? Why is this amount of biomass increasing? Well, we have observations on the ground also that have shown the same thing, just from simple photographs. So this is a photograph from Herschel Island in Canada, from 1987 and from 2013. And there's quite a big difference in this picture, and I'll highlight one particular part. The photo from 87 is not in a very good quality because it's so old, but you can see here that there's a darker green patch of vegetation in this corner, and that actually grew out to become this large shrub in this corner. So that means that this is this is what's been happening across the Arctic, that we've had shrubs that have become taller and have been expanding across larger areas. Also in the back of the picture you can see more areas where there are now shrubs that didn't used to be there. So this seems like a good thing also. While we have warming and we might have a release of permafrost carbon, the ecosystem is responding to this warming at the same time, and it's growing bigger, it's storing more carbon in its own tissue, while photosynthesis is increasing. And the jury is still out on how this will develop in the future, because these are two opposing processes, and our models actually are currently not able to show which one of these two will win in the end. But there's one thing that we can explore with models, that shrubs are in particular also changing our climate system, and not so much through an uptake or release of carbon, but the way they interact with sunlight, because shrubs also affect albedo. If you look at on the tundra like this, so I'm here standing on a hill. This is also in Siberia, and you can see all these light and dark patches of vegetation. And these dark patches, that's actually these are shrubs called betelanana or dwarf birch, and they have a much darker color than the vegetation in between, and especially the areas where there are no shrubs. So if sunlight hits this ecosystem, the amount of sunlight that's reflected will also differ depending on whether you hit these shrubs or you don't hit these shrubs. So this is a way that they will absorb more solar radiation in this way, and they can actually heat up the air locally. Now in summer there's a couple of other processes that happen also. These shrubs can also transpire more water, so if there's enough water available, they can actually then lead to more cloud formation, so that's actually a negative feedback. So in summer their effect is actually not that large, or at least not largest. Their main impact on the warming of the atmosphere actually happens while the snow is still on the ground, because you can clearly see from this picture how the shrubs are sticking out of the snow, and they're much darker than the surrounding snow. So in April and May in the Arctic we have a lot of sunlight already. These dark twigs that can absorb a lot of sunlight, and these are also the places where the snow will start to melt first. Now, you might think then that's okay, that's in northeast Siberia, but if we need to generalize this across the Arctic, and how does that work here, for example? Well, we can generalize it across the Arctic because we find the same type of vegetation everywhere. This is this betelanana shrub that had those dark patches in the tundra. And this is a picture I took in Siberia. But I've found the same shrub also in West Greenland. This is in Kobe Fjord, not too far from Nuuk. It's the same plant. I've seen the same species also on Svalbard. It's one of the most northern individuals that exists on the planet. But you don't even need to go to the Arctic. You can also just go to the Hardangervidda and you'll find the same plant. So these shrubs, when we're looking at these dynamics, we don't need to, for these the way that the shrubs themselves and how they respond, how their albedo changes the climate, we don't necessarily need to go all the way to Siberia. We can also do that kind of research here in Scandinavia and even use models to explore this. So this is actually a study that former postdoc at our section did, Johanna Ritzel, together with Frode Stordal and Anders Brun and Lena Telaksen here at the Department of Geosciences. And they used the model and they introduced, they increased the amount of shrubs and especially trees in the model. And these stick out of the snow in spring, just like on that previous picture. And you will see on the right that this is the extra heating they got in the model in March, April, May, just by introducing these taller vegetation. And also in summer, they still got a warming feedback from introducing this vegetation. This is also one of the reasons why it's not a good idea to plant trees everywhere in Norway, for example. If there is snow on the ground in April and May, that actually means that you'll be locally heating the climate, and you will, while the trees themselves might be storing carbon, and the climate feedback might still be positive. Now, this kind of warming, where we see the strong signal in the winter, it's not just shrubs that are doing this. I'd like to shift modes here a bit about for going from, so we've talked a bit about how shrubs, they can, how they store carbon in the ground and how they counteract this release of carbon from the soil. Also how they capture solar radiation and how when they're expanding, more of this solar radiation is being absorbed. But there's a large change in the Arctic that we're seeing, and that's actually happening not so much in the summer, but in the winter, because the Arctic is warming fastest in the winter. This is partly also due to sea ice decline, but also heat transport from southern latitudes. So you see here on the left the cold season from November to April, and we see this very strong warming across the Arctic. And actually the strongest warming you can see here is just around Svalbard, which is the fastest warming place on the planet. And it's much stronger warming than we see actually in summer. And this strong warming has been linked to a change also in ecosystems in recent years, because while I've been talking until now mostly about how these ecosystems have been greening and increasing in biomass, that used to be true when we look at how these ecosystems were responding to warming in the 1980s and 1990s. But when we look at more recent trends in vegetation biomass, we actually see a lot of negative trends throughout the Arctic. And the warming has continued, but the plants are not responding positively to this anymore. And this might be actually partly due to this very rapid warming that we're seeing in winter. Because just to give you an example of how extremely different the winters have become, you might think of the Arctic as being minus 30 continuously throughout winter, and this is no longer true. This is from an animation showing wind pattern and the air temperature at the surface from a bit more than 2 years ago. And you can see here the green color means that it's above 0, and the blue is just below 0. And this was actually a cold outbreak that got us very nice cold weather here in Europe and also in the US. But in, because of a very wavy pattern in the jet stream, but at the same time, this wavy pattern caused an outbreak of warm air to reach all the way up to even as far up as the North Pole, and especially Svalbard was hit very hard by this event. And this kind of event, we call these extreme winter events, they have been occurring more and more frequently in recent years. And when this happens on Svalbard in February, it's still pitch dark. The sun is barely above the horizon. But if the temperature comes above 0, we don't have snowfall anymore, we get rain. So you get into this kind of situation where rather than snow, you actually get the rain on top of the snow, it starts to mix in, and then as soon as the cold comes back after one of these extreme winter events that might just last for 5 days, then it freezes in again, and then your snow scooter is stuck in a block of ice. Now this doesn't only happen to to your snow scooter, it also happens to the vegetation, because this picture, for example, taken in the spring of 2017, shows a whole patch of vegetation encased in ice. And this means that the soils will become anoxic, and just the physical stress of being encased in ice damages these plants. This is a particular setup from project I've been working on with the University of Tromsø and the Norwegian Institute of Nature Research, where we have cameras all through Attendal and on Svalbard to monitor the vegetation and see how it's changing from year to year. This vegetation that you just saw encased, the kind of species that it is actually Cassiope tetragona, the Arctic bellheader, and this is what I'd like it to look like. Nice and green with flowers and everything, but because of these extreme winter events, we're finding these shrubs more often like this, completely dead. And this is an opposite story to that continuous greening of the Arctic that we've seen in our observations. We see actually locally that there are changes in place that can actually negatively affect these ecosystems. Now we've been to last year with my research group. We actually went to Svalbard to look at this kind of damage. So here on the right you see Jarle Bjerke from the Norwegian Institute of Nature Research, and Frode Stordal, who's sitting there, Professor Emeritus at our department. Then in the middle is Marius Lambert, who's my PhD student here in Oslo, sitting there, and Alexandra, my PhD student in Lund. And Alexandra, she's using a model called LPJGS, which is a vegetation model, and she's improving the way that the model handles snow to actually be able to simulate these kind of ice layers, and we can start to look at the interaction of how this vegetation can get damaged because of this ice. And Marius is at the same time, he's working on how does the vegetation respond to these changing conditions, and trying to put that also into a vegetation model so that the model won't, so this is a schematic of the model that he's using, Fates, and we want to improve this model in a way that it's not just if we increase the temperature, it will only show a greening, but if these extreme winter events happen, that we can actually get damage to the vegetation and some mortality also, so we get a more realistic prediction of what will happen in the future, and figure out how this affects the carbon fluxes and the surface energy balance. Now, this is still a lot of ongoing work in a model, but we have done from Lund also a lot of research on Svalbard in the last decade, measuring. And that's with this Attica Variance tower, which is a place where Norbert Pierik did his PhD. He used this tower to do very much the same kind of measurements that I did in Siberia, but then we did it on Svalbard. Norbert, he used to be a PhD student with us in Lund, and he's now actually here at the Department of Geosciences. And the kind of measurements that we do on Svalbard is very much focused on the ecosystem. It's the amount of carbon in the permafrost is not as large as in Siberia, but we can still look at a lot of the same physical processes of when the permafrost is falling, how the system is changing and how that's affecting the carbon fluxes. And especially on Svalbard, which is the fastest warming place on the planet, we will see these responses much quicker. So this is why we're monitoring this ecosystem here. Now, one of the things that Norbert figured out during his PhD was when we look at what the tower actually sees, then we see some very different patterns in the landscape. So this red cross that you see here is actually the location of the tower, and this tower is located in a valley. So the wind only comes from two directions mainly, and from the northwest and from the southeast. And from the northwest, you can see here that it's you see a little pond, and the vegetation is actually a lot better than the vegetation to the southeast. So these circles, by the way, that are drawn here, they show what the Attica Variance Tower is seeing, which part of the landscape. So that's 25% of the flux will be coming from here, 50% will be coming from here, and 3/4 of the flux influenced by this outer circle. So, the nice thing about this butterfly pattern is that you can actually then separate these fluxes into these two different areas. And that's what he did, and that's what you see here on the right side, where the red line shows the southeastern sector, and the blue line shows the northwestern sector. And this is, again, the same variable that I would be measuring in Siberia, the net ecosystem exchange. So the more negative it is, the more uptake of carbon. In the drier part, we see that it's not as negative, so there's less uptake of carbon actually happening in this drier part than in the blue part. So this means that the amount of wetness in the landscape has a tremendous control on how much carbon is being taken up or emitted by the ecosystem. And actually, what Norbert also found out, that in this wetter part, it's also, there's both photosynthesis and respiration are more active. So this is also a more active system than this drier part. Now, in the background, you can see all these nice patterns that you might have wondered what it is. These are ice wedge polygons, which are very typical features that are found across the Arctic, which form from the freezing and thawing of the ground, and you get these cracks in the ground. And in the center of these polygons, you can often get these very wet features. And on the rims, you can, just a few meters away, you'll have these very dry vegetation. And you can get these very strong contrasts within the landscape over very short distances. And to just show you some of that complexity of this system, because that's what you need to capture when you're doing these measurements. This is a drone video that Norbert did around this time of year, so you'll see the vegetation completely brown. And here you see the nearby river, the Attica, and then here we're going towards the actual platform. And you can see here already, that's actually the Attica Variance tower right there. And on the next shot is a little bit lighter. So here you can see all these differences in the landscape and how complex it actually is. And the light brown parts are wetter, and the grayer parts are drier. And so this is the kind of complexity that you're dealing with. And an Attica Variance tower will give you an integrated signal over this landscape. So in a broad sense, you'll know what's going on, but you won't know exactly where this different flux is coming from. So when we do this kind of measurements, we're also using flux chambers that you see here on the right that do measurements at a very on a small scale, and we can look at the processes in detail. But it's also very laborious. So it means that you need to put in a lot of effort to actually measure this. So we're also trying to get in some other tools to capture what's happening on the ground and track this over time. And then, just like the drone is showing, that the best way of doing that is actually if you do that from above, because then you'll actually see what's happening. So that's why we turn to remote sensing. So here's a picture of Afvendalen on Svalbard. So on the top left there, you can see Longyearbyen. And our site is here in the middle. This is actually an aerial photograph taken from the valley. And if you can't do this everywhere, of course. You can't fly an airplane each time you want to have an overview of your site. So, and you want to do this in a consistent way also. So over time, it's best to use satellites. Now, one of the most used satellites to track how ecosystems are changing across the world is the MODIS satellite. But if I'm now going to show you what this valley looks like in the MODIS satellite. It's a 20-year-old satellite, has a very long time series, but it's rather coarse. Because the valley looks like this in the data set. You can still make out that there are some mountains with snow on top and that there's a valley, but where the ecosystem is or these ice wedge polygons, that's not visible at all. Just to give you a better idea, we'll zoom into where the site is and you only get this picture. So I can still use the satellite over time to see how it's changing, but I have no idea actually what I'm looking at. Whether I'm looking at the river, am I looking at these wet polygons, am I looking at these dry polygons, I'm not sure. Fortunately, technology is progressing. We now have a much higher resolution satellites, so for this same area, we can now get a picture like this from the Sentinel-2 satellite, which has a 15-meter resolution. And now we can start to see some detail. We can actually see a road here and clearly see where the river is and then find out where our ecosystems are. But also with this satellite, it's only been around for a couple of years, so if I want to have a long time series, it's not there yet. And I want to know how the system is changing now. So we need to have even higher resolution data. So I'll zoom in to this part, and then you see actually on the Sentinel data, it's still a bit of a blur. Again, these ice wedge polygons are hardly visible. If you look very closely, you'll see some darker pixels here that are some ponds that show up, but otherwise it's not a lot of information I'm getting here. So we need to go to even higher resolution satellite data like this. This is the same area as in the previous picture. And then you can suddenly see all these nice ice wedge polygons. I can even see where the Attica Variance tower is, and I can see my boardwalk here. So this is the kind of detail that you need. But when I looked up the data for this particular location, I only got an image once every 2 years, because this is a very cloudy location and these satellites don't come over that often. So this is a problem where I have this very high detail of the landscape, but I don't have the overview in time. So, and I want to zoom in actually even further than this. So, because if you, let's zoom in here, I can see sort of what's happening here, but I know what's going on there because I've been there. And going there is maybe the best way of finding the spatial information, because you can throw up a drone in the air and actually let it fly around. And so for the same area, if I use a drone, I'll get this picture. And now I can get the full detail that I need from this ecosystem. This is a false color image where the blue has been replaced with what the drone sees in near infrared. And then you see also that the vegetation shows very strong contrast in the system. So the dark red means there's much more biomass. But I can also see a power line going here, and I can see even footsteps here. So I can get really that detail that we need to figure out what the landscape looks like. And if you do this over, say, a growing season a couple of times, you get the changes in the landscape, and you can compare that with your Attica Variance data, and you will be able to find out exactly how that landscape is changing over time. So to conclude, when we look at these systems, at Arctic ecosystems, we have observations, and they provide us with process knowledge. And then we can use drones to sort of find the signal in the noise. But at the same time, we have satellites that can maybe are not, can be difficult if you just point them at one location, but if you use them for the entire Arctic, they will show you this large overview. And if you put all this together, you can get a better understanding of how these ecosystems are changing, how they're responding to climate change, and how they might influence the climate in return. And we can put that into models, and they can show us a possible future. And with that, I'd like to thank you for your attention.
Thank you very much, Frans-Jan, for taking us through this very interesting and a bit scary story about what's happening in the Arctic. It's already 1 o'clock, and I think there's no room for questions, but Frans-Jan, he's still here, so it's possible to talk with him. And for those of you that are watching on YouTube, you can, on the Science Library YouTube channel, you can also take contact with Frans-Jan and discuss with him later. So thank you everyone for attending. Next time is in mid-October, still a secret what that is, the program. Okay, thank you.